13. Which process can be used to separate a mixture of two liquids having different boiling points? Well, if they have different boiling points, they have different physical properties. They are different substances for sure. Okay, so we want to separate a mixture of two liquids based on their boiling points. Well, we can't separate a liquid by filtration. Come on, you can't filter one liquid out from another. It just does not work. Okay, when we do filtration, we're separating a solid from a liquid and it's getting trapped on the filter paper with its very tiny pores. Okay, sublimation, you should be aware, is when a what? Solid goes directly to a gas. That's what dry ice does, right? If you've seen that in your class, CO2 solid goes to CO2 gas. Deposition is another phase change that you have to know, and that's when a gas goes directly to a solid. Snowing is the greatest example. But that's not a separation, that's just a phase change. So if we're just eliminating choices that make no sense, we're left with distillation. But what is distillation? Okay, well, it's where we put, and I guess the famous example of distillation, besides separating crude oil into gasoline, natural gases, kerosene, and diesel fuel, besides that is when we ferment something. For instance, if I take sugar, okay, and add it to some solution with yeast, and basically we make alcohol. Alcohol gets developed. And what we do is we heat off the alcohol and we make liquor from this distillation process because the alcohol will evaporate before the water does for the most part, and that evaporated alcohol will condense as it cools into alcohol droplets. So we can separate the alcohol from the mixture of yeast and sugar if we're, using grains of those things. And I talk about this thing called fermentation because it's something you should be aware of. We ferment, we get alcohol from fermentation, and it's a reaction you have to know where we take a sugar like C6H12O6. Okay, and that could be from grapes. If it's from wine, it could be from, if you're making whiskey, it's from grains. And basically we make two CO2s and we make two ethanol molecules, C2H5OH. Okay, and the ethanol is of course the alcohol that is in our wine, liquor, and beer. And how do we separate that alcohol from the mixture? We distill it, we heat it. And because the alcohol boils at a different temperature, much lower than the water and the rest of the, when we say mash, it boils off first, and then we're able to condense it and collect it away from the rest of the material. And in essence, it's the same way we separate diesel and kerosene from crude oil, although they use fractional distillation, but the same concept is held. Number 13 is 2. On to number 14. Number 14. Which name describes a solution of sodium chloride in water? So you hear the word solution, ding, ding, ding. That should represent something you already know. A solution, that's a sodium chloride. So sodium chloride is NaCl. The naming of sodium chloride, notice the ID ending is for the binary, that's two different capitals. Metal, non-metal, this is ionic. Okay. And it's NaCl, and if it's a solution, we write aqueous. Now, what does that mean? This is really important, party people. This means that this solid has been dissolved. Okay, in water. So when you hear the word solution in water, we know that the water surrounded the sodium ions in a way that it could actually get in between the water. And you have to draw this, okay? You have to be able to do this for different parts of the test or recognize it. Sodium is +1. You can look that up. And chlorine is -1. And water has a negative end, which is the oxygen, the more electronegative end. It will attract and surround the sodium ion this way. And the positive part of water will surround the chloride ion. In this way, these ions get pulled apart and they intermingle, okay, and get dissolved. So you hear the word solution, you think dissolved. You also think when something dissolved, it is homogeneous. Anytime you make a solution, you have a homogeneous mixture. Okay, so anytime you hear of a solution, you know you've got an AQ. You know it's dissolved. You know water is able to attract it and break it apart evenly so that the first drop is the same as the last. Okay, so we know it's homogeneous. By the way, if it was heterogeneous, it'd be insoluble with water. It wouldn't have an aqueous, and you wouldn't say the word solution, okay? You'd have some stuff on the bottom or floating on the top that you can filter out. But this is going to make a solution where there's no solids appearing because they get in between the water, as I'm showing you with these molecule ion attractions. Okay, now who's the water, who's the solvent, and who is the solute? The substance being dissolved is the solute. So the solute is NaCl. The solvent, these are the chemicals doing the dissolving. They're dissolving by surrounding the ions. Okay, of course, is the water. The solvent is the water. And for those reasons, number 3 is your answer. On to number 15. Number 15, at STP, standard temperature and pressure, given to you in Table A, which property would be the same for a liter of helium and a liter of argon? Okay, so they've got the same volume. What else is also the same? If temperature and pressure are held constant, well, it's at STP. Man, this is Avogadro's hypothesis that stated if you've got two different gases, and we do, under the same conditions of temperature and pressure, hey, they're at STP. They're telling you that. They don't have to be at STP, but they have to be at the same temperature and pressure. You're going to have the same number of particles. Same volume, same number of particles. Now, Avogadro, Amadeus Avogadro, called a particle a molecule. So a lot of times these questions will say same number of molecules. Now we know something about helium. It's a noble gas. It's very stable. It has a completely filled outermost shell. So they don't bond. So helium is just particles that hang out by themselves. Argon has the octet rule. Its outermost shell is filled as well. Or at least it has the octet rule to show it's very stable. So it's also a single monoatomic particle. So same volume, same number of particles. Okay? A lot of times you'll hear the word molecule. And of course, if this was H2O or CO2, we would use the word molecules because the example they gave me were noble gases that don't bond with anything. Therefore, they're going to just hang out by themselves and just be atoms. It's the same number of atoms. Careful with the atoms answer, okay? Because just as if I do this, if I was to compare CO2 and H2O, okay, not a great example. How about if I do something else? How about if I do CO2 and HCl? These are both gases. Okay. Now, if they're both 1 liter, okay, and they're both the same conditions of temperature and pressure, they will not have the same atoms. You can see that for every 1 particle, there are 3 atoms here, and this particle, there's 2 atoms. And I'm counting capital letters for different elements. Okay, so careful with that. So in any case, 15 is 4. I call this the same problem. Okay, and it comes up a lot. It's Avogadro's hypothesis, but I call it the same problem. Same volume, same temperature and pressure, same number of particles. Normally it's written same number of molecules. Okay, any case, number 15, the answer is 4. Okay, mass, density, and boiling point are not what the Avogadro's hypothesis is about. So on to number 16. Number 16, the melting of an ice cube. Melting, that's a phase change. Is an example of what? Well, all phase changes, my friends, are physical changes. You have to have that down. So, ice cube is ice, it's water, it's H2O, solid, and it's going to go to H2O, liquid, or liquid. Liquids have more energy, so that's solid, I got a liquid. Now, my friends, that's a physical change. Why? Because the chemical formula is not changing, right? If you were to break bonds and then reassemble and make new bonds, that's a new substance being made. That's new properties are showing up. All of a sudden you see bubbles, a color change. But here the chemical formula is staying the same. So you got to know that, okay? All types of phase changes, okay, are all physical changes. You're not breaking bonds, you're breaking intermolecular attractions. Now, is it endothermic or exothermic? Does it require energy or is energy released? You need to know that endo is absorbing. So I always think about the heating and cooling curve. So if I give you the heating curve, the best that I can do here, this is the solid phase. At a phase change, the temperature stays constant or the kinetic energy remains constant, but the potential goes up because we're adding heat at a constant rate. And eventually it all becomes a liquid and the liquid goes up. So the solid going to a liquid, that's the phase change. We should all remember the phase change is where the temperature or the kinetic energy stays constant, but the potential energy in this case is going up. Why? Because the kinetic is being converted to potential. Well, back to the problem. If this is how we're going, and the way to remember this is liquids have more energy than solids. We know that liquids have more degrees of freedom. They don't have to stay in a crystal pattern. So we know that to go from a solid to a liquid, we have to climb an energy ladder. Liquids have more energy than solids. We know that liquids, you have to melt them. You have to melt the solid. You have to add energy. My arrow is going up. This is an endothermic process. This curve is going up. Why? Because we're absorbing energy. We need energy to melt. And we know it's endothermic because you should also know that endothermic makes the environment become colder. That's important. You drop ice cubes in water, it takes the heat from the water and your temperature of your system drops. But in any case, the energy would be written on the reactant side. This is the reactant side. Needs energy to go forward. Liquids have more energy. And so if I have higher energy here and I have lower energy, the only way to make this work is to add energy. The curve is going up. It's endothermic. All right, so you have to know that solid to liquid, you need energy to go to a higher energy state. It's endothermic. So number 2 is your answer here. All right, on to number 17. Number 17, which statement explains the low boiling point, which means the low amount of energy needed to have a phase change of a liquid going to a gas at standard pressure. So I guess they're asking, why does hydrogen, H2, boil at such a low temperature? Why doesn't it need a lot of energy to go from what? H2O liquid into H2O gas, higher energy. Of course, it's endothermic. It needs energy to go up because gases have higher energy. But the point is, why is it so low? Well, the first thing is to understand, party people, is that this is a phase change. It's physical. The chemical formula is not changing. And if the chemical formula is not changing and it's physical, we are not breaking chemical bonds. We are not forming chemical bonds. We don't have any chemical change. So any use of the word bonds makes these choices incorrect. We're not breaking the bonds here. Party people, this is an H bonded to an H. And it's going to what? An H bonded to an H. We're not breaking the bond here. What this more looks like is if I have two hydrogens bonded together in a liquid, liquids normally have a higher density as they attract each other more. And then when they become a gas, they overcome these attractive forces. This would be van der Waals or London dispersion forces or weak nonpolar forces. These gases, when you give enough energy, overcome these attractive forces. They have a heck of a lot more energy and they exist much farther away from each other. You are breaking intermolecular forces here. That includes the weak forces of nonpolar attractive forces, dipole forces, or H bonds. Okay, so we are breaking intermolecular forces, and if it boils at a low temperature, boys, these must be weak. If you don't need much to break these forces to get them into a gas, they've got to be a weak intermolecular force. You have to know that in a phase change, we're not breaking bonds. We're breaking intermolecular forces, which, by the way, are always weaker than bonds. Do never mention bonds breaking during a phase change. Why? Because we're not making a new substance, because we're not breaking bonds and reforming a new one. So you should also know that low boiling points always have weak intermolecular forces. We have a table, okay? Table H, okay, is a vaporization table, has vapor pressure curves. And as temperature goes up, some liquids vaporize easier. So this would be A and this would be B. And we would say that if you look at the same temperature, temperature is written on the bottom here. As temperature goes up, these arrows go up because they vaporize more. But if I pick one temperature, whatever that temperature what it is, you can, whatever it might be, A has a higher rate of evaporation or vapor pressure than B at the same temperature. So why does A have a higher vapor pressure? Weaker forces of attraction. And by the way, if the atmospheric pressure, which is written in a dotted line, equals the vapor pressure, you got boiling. Who reaches this line first? Well, A does. A has a lower boiling point. Things with a lower boiling point have weaker attractive forces. That's these concepts here. So for those reasons, 17 is 4. On to number 18. Number 18. In a chemical reaction, which term is defined as the difference between the potential energy of the products and the potential energy of the reactants? This is a straight definition, but like things, you can infer this from your potential energy curves. So let's just say we have an exothermic reaction. This is a curve that measures potential energy. That's the energy that's in the chemical bonds, and this will be a time coordinate. So over time, if we start with some reactants, okay, these would be my reactants, and when the products are made, in this case, and I'll write them in, so this would be reactants. And these would be products. Okay, now, party people, we're going to have a little pathway here. We're going to have a potential energy curve, and we should know the difference of where we start and finish. The difference where we start and finish is the change. I can do this. Not the greatest straight line, but this difference right here of potential energy is called the delta H. So think with me for a second. This is an exothermic reaction. The products have less energy than the reactants. Why? Because heat was given off exothermically. So delta H is going to be a negative sign because it's going down. But what is delta H? It's the heat of fusion. Well, what's the definition? Well, if this was a value of 20 and this line here was a value of 100, and this would go down negative 80 kilojoules or something. How did that happen? We need a negative to show that energy was released or the energy change went down. We would take the what? Potential energy of the products, 20, minus the potential energy of the reactants, right? That's the reactants' potential energy is all of this right here. That's 100. And that'd give you a negative 20. I'm sorry, negative 80. I can do the math. Okay, negative 80. So don't forget, party people, potential energy of the reactants is this line here. That's too big of a line. Wow. Okay. And the potential of the products is this line. All right. So again, potential energy of the reactants is the energy all the way up to this point. This is the potential energy of the products. And then the potential energy of the what? The change in potential energy between those 2 points is delta H because it's going down. It's negative. We want to show the negative to say energy is released, so we subtract those two values. Okay, products minus reactants. Okay, and people get lost in potential energy. These are all potential energy curves. And if we keep going, by the way, this would be the activation energy of the forward. This would be the potential energy of the activated complex, right? So in any case, just a couple of things that you should be aware of. So this is a straight definition problem, but you can infer it based upon your potential energy curves. Any case, for all those reasons, okay, the correct answer is number 1. Heat of, oh my gosh, not heat of fusion, heat of reaction, number 2. Okay, heat of fusion is the energy needed to melt something. Okay, all right, so 18 is 2, on to number 19. Number 19, which phrase describes what happens to a reaction pathway and activation energy of a reaction to which a catalyst is added? So what happens to the activation energy? We all should know that activation energy is lowered, but what does it look like on a potential energy curve? Okay, so we draw a potential energy curve. I'm going to do an exothermic reaction. The reactants have higher energy than the products. We have this pathway. I'll draw the pathway in blue here. And we know that if we add a catalyst, we're going to change that pathway. It's called an alternative pathway. So it lowers the hump, but does not change where you start and where you finish. So it doesn't change delta H. Don't forget the difference where you start and finish. Okay, this arrow right here is delta H, and for an exothermic reaction, it's negative. But what does a catalyst do? A catalyst lowers that hump. And now what is that hump? Well, the difference of where you start to the top of the hill is called activation energy. Think about it. You love to ride slides. This is a slide. Well, you have to climb it. The energy you need to put in to get to the top, then you can just spontaneously move down by yourself, by gravity. So this is the activation energy. But if I add a catalyst, now my activation energy is a lot smaller. The top of the slide is a lot smaller, which means, of course, I can get a lot more rides in for the same energy. That's how it works. You should also know that it increases the rate of reaction. You get a lot more collisions in, effective collisions with the same energy. So don't forget that the pathway is from where you start into where you finish, and so it's going to be a different pathway. This red line here, okay, this red line that I drew right here is a different pathway. So it's a different pathway, and of course it's a lower activation energy, okay, because you need less energy to get to the top. Right? So think of the analogy for a reaction to go. You can't just walk up to a slide, you got to climb the slide. And if I lower the slide, there's less energy I have to put into to start my ride, less energy to put into to start the reaction. Okay, any case, that's what activation energy is. 19 is 4. On to number 20. So number 20, an atom of a which element is bonded to a carbon atom in the amide functional group? So what's the name of the group or the class? Okay, in this case, they don't want the name of the group, they want the element that makes it the amide class of functional groups. So there is a table here, my friends. Table R is your friend. So very straightforward. So let's go to table R. So here's table R in all of its glory. We're going to go find the amide. And so I go find the amide, or was it an amine? I losing track at this point in my life, but all I know is that amine, I think it was an amine, it's a nitrogen. Okay, if you notice, the nitrogen is bonded to the carbon. Okay, and same thing for an amide as well. Nitrogen is bonded directly to a carbon. They give you an examples, guys. Okay, so nitrogen is what's bonded to a carbon right from the reference table. All right, so it was an amide, but bottom line is it's the nitrogen, okay, right from table R. So number 20 is 2. On to number 21. Okay, number 21. Which statement describes two isomers of butane? Isomer. Iso means same. Okay, just like we hear of isotope, same element, different number of neutrons. But isomer is same molecular formula, same number of carbons, hydrogens, and oxygens are same number and type of atoms, but different structure. So here's an example of two isomers, and whether it's butane or they're isomers of another compound, they're going to have the same molecular formula. Let's count. We have 1, 2, 3, 4 carbons, C4, and then we count the what? The sticks are H's. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's H10. And this one is C4. And if we count the sticks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, H10. Remember, the sticks are hydrogens. So these both have the same molecular formula, but they have a different structure, and that is what these are called. These are actually called structural isomers. There's different types of isomers, but for this course, structural. So they have the same molecular formula, but different structural formulas. And by the way, because of their different structural formulas, they will have different properties that you must know. And because of that, they actually will have different names, right? So this is actually called butane, the one above it. But for 4 carbons in table what? P. Ane in table Q for the single bonds between the carbons. This one right here is going to have a 1 carbon group attached to a 3 carbon chain. So this is a prop for the 3 carbon longest continuous chain. There's single bonds between the carbons, so that's an ane. But there's this methyl group, this 1 carbon group, and it's in the middle carbon, so to be on the 2nd carbon, we would say 2-methylpropane. 2 different names for the same molecular formula because they have 2 different properties. Okay, I mean, the properties weren't part of this question, but they will be in some other questions. Again, I'm trying to teach you the concepts behind every question, not just what the answer is. So the best answer here is the same molecular formula, but different structural formulas. What's a structural formula? This is a structure, shows how they exist in 3 dimensions, or at least 2 dimensions, right? So in any case, 21 is 1. On to number 22.